In this video, we will be talking about how to calculate a to the power b modulo some value mod. In our example that we'll be using, we will use the value 10 to the power 9 plus 7 because that is the most frequent modulo that is given in problems. But generally speaking, for binary exponentiation, you don't need the modulo to be any prime. You can use any modulo that's possible. Okay. So let's say you take input a and b and you need to find the value of a to the power b modulo 10 to the power 9 plus 7. So this is how you can also write 10 to the power 9 plus 7, 1e9, that is 10 to the power 9 plus 7. Okay. So this method tries to calculate a to the power b modulo mod. Okay. So this is the generic method. So how do we do this? So if you remember the way of binary exponentiation, we'd be doing it in an iterative fashion, and let's say we have some binary number like this, okay, and we need to find the binary exponentiation. So we declare an answer equal to 0. Let's say this is your answer, and initially the answer is equal to 1. Why? Because you'd be multiplying a lot of a to the power 2 to the power k format numbers, right? If you remember, like whichever is relevant, you multiply that there and there. So all of those numbers will be multiplied to 1. So that's why you initially keep answer to be 1. Now if b modulo 2 equal to 1, now what does this mean? This means, this part of the code means that whether the last bit of the number b is 1 or not, because everything above this is divisible by 2. So taking a modulo 2 means that whether it's odd or not, and the last bit basically defines whether the number is odd or not, right? So this is what we would be using to calculate the last bit of the numbers. Okay, so let's look at the algorithm that we would be using. So while b is positive, like till the point when b is positive, okay, so if you don't write greater than 0, that's fine, because once it becomes 0, it will remain 0. So once it gets 0, it terminates. Okay, while b is positive, if b modulo 2 is equal to 1, if the last bit of b is 1, then you multiply a to the answer. Okay, and whenever you multiply things, just to be safe, you also use this modulo, right? Because that's how modulo operations work. Whenever you multiply, just make sure you do a modulo. Okay, now a is equal to a into a mod. Okay, so then if we have correspondingly added the contribution for this, we multiplied a to the a into the answer, and then we divide this number by 2 and square the number a, right? So we square the number a and divide the number by 2. Okay, and we keep on doing this until b is positive. Then again we come to this number, we see that this is 1, so we multiply a square. So then this, when this was this, you first multiplied a, then you divided it by 2 and you made a equal to a square. So now when you multiply a, that is actually a square, right? So when you then multiply this number, this is actually a square. Then you divide this by 2 and you make it a 2 to the power 2 to the power 2, that is a to the power 4. But then this is 0, so you don't multiply. Then this becomes a to the power 8, and then you multiply a to the power 8 because that's 1, like that is odd, right? And then it becomes 0, and then you terminate. So this is the number, right? And you can see that this is actually multiplying the binary powers of the number 1 1 0 1, right? 1 here, if you can see that. And then once you are done with this, you return the answer. So this is the iterative way of finding a to the power b mod. But there is some things to be taken care of in this implementation. Now let's look at that. Now our modulo is pretty large, right? 10 to the power 9 plus 7. Let's say our answer was 10 to the power 9, because that's possible, right? After some multiplying some bunch of numbers, you got 10 to the power 9 modulo mod, and then a is also 10 to the power 9. Okay, so if you multiply these two numbers, this will become 10 to the power 18, right? So if answer is integer, this will overflow, since a is integer and answer is also integer. So this is going to overflow then and there, and then if you modulo that, that's not going to help you, because once the number overflows, the answer is going to get wrong. So if you are multiplying two integers and it's overflowing the integer range, you cannot multiply like that. So what you have to do is that you will have to multiply one LL to that. Okay, so multiplying one LL is actually making this to typecast to long long. Okay, there is a data type called long long which has a limit up to 10 to the power 19. Okay, so you can use one LL multiplied by answer multiplied by A. So this will typecast everything to the long long domain, and then since in long long this is feasible to multiply, like it will be first this and it will become long long, and then you multiply it with A, so it will become long long. So in long long 10 to the power 9 and 10 to the power 9 will fit in long long, right? And then if you take a modulo, that will reduce it back to some smaller range that is less, that will fit in integer, and then you give that value to the answer which is an integer. So that's fine because that's not overflowing. Again over here A is an integer, but A square might overflow, right? So again you do the same thing, you multiply it with 1 LL, right? Okay, and even if you don't give this bracket, that's fine because expressions are evaluated left to right. So even if you remove this bracket, that's fine because first this will evaluate, then this will evaluate, and then this will evaluate. Multiplication and modulo all are in the same precedence order, so that's not a problem, but still. Okay, and once you keep this code works in integer quite well, right? Like even if all the things are integer and the answer is integer as well, this will work. Okay. Let's say we didn't want to multiply this integer 1 LL to all these calculations. So what we could have done is use the data type long long in the method itself. So you can create a custom data type LLI which is same as long long integer, okay, using this notation, and we can keep the parameters like this, something like this, okay, and we can return LLI, and in that case you won't need to multiply things like this, right? And also keep the answer in LLI, like that is long long. So now every variable is long long in itself, so nothing will overflow, right? So that will not be a problem. Mod can be integer, you can even keep that in LLI. Okay, so keeping things in LLI is safe since it will not overflow, but only if you are taking modulos properly. If you like miss out modulo in some space, it will overflow and then you won't get a correct answer. Okay, so let's quickly try and run this code. Okay, so let's save the code. Okay, okay, so now we have two numbers. Let's say we want to calculate 2 to the power 3, that is 8, right? Because 2 to the power 3 is 8 and 8 is less than this modulo, so it will not wrap around, right? But if you want to calculate 2 to the power 100, sorry, we need to run this, and then 2 to the power 100, that is some large value. Okay, that's some large value, and this is of order 10 to the power, this is less than 10 to the power 9, as you can see, because everything got rounded off, like everything got moduloed 10 to the power 9 plus 7, so everything is less than 10 to the power 9 plus 7 for sure. Okay, so this is how you can implement binary exponentiation in iterative fashion. There is a much simpler way to understand things in recursive as well, but iterative code of binary exponentiation is faster than the recursive one, so try to use the iterative version of the code. That's all for binary exponentiation. Let's quickly have a look at how would you calculate the inverses of numbers. So if you remember, if you had to calculate A inverse mod some prime p, this is actually same as calculating A to the power p minus 2 mod p, right? So if you had to calculate the inverse of A, let's suppose in this example you could have calculated binary exponentiation of A, whatever the modulo is. Let's take this modulo itself. So this modulo minus 2, right, mod minus 2, and the same mod. Okay, So let's quickly have a look at that. So we won't be needing two values, so let's quickly remove these. Okay, so we would take a and just print out the inverse of a modulo this value. So as you can see, we need to compile this once more. Let's say you need to calculate the inverse of 2, and that is this number, right? This is 5 into 10 to the power 8 plus 4. And if you see, if you multiply this with 2, you get 10 to the power 9 plus 8. Okay, this you get as 10 to the power 9 plus 8, and 10 to the power 9 plus 8 is just one more than this. So if you take a modulo, it is 1. So this multiplied by its inverse is actually 1, right? So that means this is a correct inverse. So this is how you can also use binary exponentiation to calculate inverse in order log n. So since this took only, so every step you are dividing it by 2, this will terminate in order log b number of terms. So you can calculate the exponentiation in order log of b. So for any prime p, when you need to calculate this inverse, this will take order log of p. Okay, so now you can code binary exponentiation for calculating a to the power n kind of stuff, and also you can use the same method to calculate inverses of numbers whenever needed. Okay, so that's all for this video. Thank you.